Hello, I am Ravi Kumar. I will be taking this course on refrigeration and air conditioning. But before we start this course, I would like to review the concepts of thermodynamics. Because thermodynamics is a very wide area and it cannot be covered in one lecture, I will cover only those parts of the thermodynamics which are relevant with this course. So, topic to be covered in this lecture are definition of thermodynamics, basic terms in thermodynamics, laws of thermodynamics, and thermodynamic processes. Now, we will start with the definition of thermodynamics. The thermodynamics is the science encompasses the study of energy, its transformation, and relationship amongst the various physical quantities of substance which are affected by or cause these transformation. Basically, thermodynamics is the study of energy. It deals with the heat and work interactions and their effect on different physical quantities like pressure, temperature or volume of the system. There are certain terms in the thermodynamics which need to be defined here. First is the system. System is the prescribed region of space or finite quantity of matter surrounded by an envelope called the boundary. So, any region in the space on which the thermodynamic studies are focused is called system. Now, the system, there are three types of system. One is closed system. In closed system, there is only energy interaction with the surroundings in the form of heat and work. There is no mass transfer across the system boundary. In closed system, in open system, there is a energy and mass interaction with the surroundings. So, open system is like a wire mesh box. Suppose there is a wire mesh box kept in the space. So, in a wire mesh box, the energy transfer and mass transfer both can take place. Now, the third type of system is isolated system. In isolated system, there is no energy transfer, there is no mass transfer. For example, this room. So, if I close all doors and windows of this room will become a closed system. Okay. So, if the outside temperature is high, the heat can be transmitted to this room through the walls of this room. So, energy interaction is possible, but mass interaction, mass transfer across the room wall is not possible. At the same time, if I open the doors and windows of this room, there will be flow of air across the room through the windows and room becomes an open system. Now, in the third case, that is isolated system. In isolated system, if I close all doors and windows of this room, if I insulate the room walls and the roof, in that case, there will not be any heat transfer across the room wall, there will not be any mass transfer across the room wall, and room becomes an isolated system. Anything outside the system is surrounding. Anything existing outside system is surrounding, and system and surrounding together they make universe. Now, work. In thermodynamics, the work is defined as the work is done by a system if the sole effect on the surrounding could be raising of weight. So, in the thermodynamics, if any process, the sole effect of the process is raising of the weight, it means the work is being done. Now, heat is sort of energy. So, heat is the energy in transition by virtue of temperature difference. So, through temperature difference, any transfer of energy is called heat transfer. And in engineering practice, we deal with the engineering heat transfer, because in engineering practice, we do not deal with joules and kilojoules. When we say heat transfer is there, heat transfer means it is in terms of watts and kilowatts. So, we are more concerned with the heat transfer rate in engineering practices rather than the heat itself. So, whenever we say there is a heat transfer, it means there is a heat transfer rate or transfer of heat in the form of joules and kilojoules per second. Now, property. Measurable characteristics describing the system that depends on the state of the system and is independent of the path by which the system arrived at the given state. The property of the system can also be driven from the measurable characteristics of the system, for example, enthalpy and entropy. And in order to describe a state of the system, we require minimum of two properties of the system. Now the properties are classified as intensive property and extensive property. Now intensive properties are those properties of the system which are independent of the mass of the system. For example, temperature. In a room, whether the mass of the air is 5 kg or 6 kg or 7 kg, the temperature is not going to change with mass. So the temperature is going to remain constant. So there are certain properties like temperature, pressure. So these properties are, or entropy, specific entropy, not entropy, specific entropy. So these properties are intensive properties, and there are certain properties which are extensive properties. Now extensive properties are those properties which are dependent upon the mass of the system. For example, kinetic energy, potential energy. So these type of properties are extensive properties. Now state of the system is the unique condition of system at an instant of time described by its properties. So state of the system is described by properties, and in order to describe state of the system, minimum two properties are required. Now another term is the process, the path of successive state points through which the system passes during transition from one state to another state, called a process. Suppose a system passes from state 1 to state 2 through different successive states. So these different successive states together, they form a process. Now cycle or cyclic processes. Cycle is a combination of number of processes. Suppose there are number of processes starting from 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 1. So initial state of the process 1 and the final state of last process are same, then this is known as cyclic process, or this is known as a cycle, thermodynamic cycle. Now work in thermodynamics, there are two types of work. One is boundary work, another is shaft work. Now boundary work comes into the picture when there is a closed system as shown in the figure. In this figure, a piston cylinder arrangement is shown. In this piston cylinder arrangement, the boundary is shown by the dotted red lines. Now if I give heat to this system, the piston will move upward direction, and piston carries weights also, and piston will move in upward direction. But there is no mass interaction with the surroundings. So this heat transfer to the system, because there is a movement in the system boundary. So in this case, work is done by the system. So the boundary work is always integral of PdV. So in order to have boundary work, there has to be change in the volume. If there is no change in the volume, there shall not be any boundary work. Now another type of work is shaft work. Now the example of the shaft work is air compressor. Air compressor, there is no movement of the boundary, and low pressure air enters from the one side and high pressure air leaves from the other side. And this pressurization of air is done with the help of a motor, and because work is done on the system, here the shaft work is equal to minus VdP. Work is done on the system, and if there is no pressure change, in the shaft work, in that case, if there is no pressure change in the open system, the shaft work is 0. So in order to have shaft work, there has to be a change in the pressure. Same is the case with the boundary work. If we want to have boundary work, in that case, there has to be change in the volume of the system. Laws of thermodynamics. So there are 4 laws of thermodynamics, starting from the 0th law, 1st law, 2nd law and 3rd law. They are not numbered as 1st, 2nd and 3rd and 4th law of thermodynamics. The reason being that it started with the fact that when we learned that heat can be converted into the useful work. But is it possible to convert entire available heat into the useful work? Suppose we have 100 joules of heat. Is it possible to convert 100 joules of heat into the 100 joules of work? That is not possible, and it is stated by the 2nd law of thermodynamics. Now, the first law of thermodynamics speaks about the conversion of heat into the work, because when we say can we convert 100 joules of heat into the 100 joules of work, first of all we have to ensure can we convert heat into the work. So, first law of thermodynamics says that we can convert heat into the work or work into the heat. And zeroth law is the most fundamental law, and it came after the around 50 to 60 years after the introduction of the first law and second law of thermodynamics. And zeroth law of thermodynamics speaks about the it gives the concept of temperature. It's the most fundamental law and it gives the concept of temperature. Now, zeroth law, we will start with the zeroth law of thermodynamics. Now, the zeroth law of thermodynamics states if two thermodynamic systems are each in thermal equilibrium with the third, then they are in thermal equilibrium with each other. Now, here I would like to distinguish thermal equilibrium with thermodynamic equilibrium. There is one thermal equilibrium, another is thermodynamic equilibrium. Now, these two equilibriums are different. Now, in thermal equilibrium means there is no transfer of heat between two bodies. Then if there are two bodies are in contact with each other and there is no heat transfer between these two, or there is no energy interaction between these two bodies, they are called to be in thermal equilibrium. But when we talk about thermodynamic equilibrium, it includes the mechanical equilibrium and the chemical equilibrium. It means the system should not have any unbalanced force. At the same time, system should not have any unfinished chemical reaction. So, now we will go back to the zeroth law of thermodynamics. So, when system A is in thermal equilibrium with system B, A is also in thermal equilibrium with system C, then B and C are also in thermal equilibrium. It means if the temperature of A, it is derivative of the zeroth law, that temperature of A is equal to temperature of B and temperature of A is equal to temperature of C, then temperature of B is also equal to the temperature of C. Now, we will come to the first law of thermodynamics. The first law of thermodynamics states that in a cyclic process, the cyclic integral of heat transfer to the system is equal to the cyclic integral work transfer to the surroundings. So, the first law says cyclic integral of heat transfer to the system is equal to cyclic integral of work transfer to the surrounding. Now, in thermodynamics, when heat is given to the system, it is taken as a positive heat transfer. When heat is extracted from the system, it is taken as a negative heat transfer. Similarly, when the work is done by the system, it is considered as positive, and when work is consumed by the system or work is done on the system, the sign is negative. Now, in this case, now the statement of the first law of thermodynamics does not say anything about the internal energy. The concept of internal energy is derivative of the first law of thermodynamics, and this is how it is done. Suppose there are two states 1 and 2. From state 1 to state 2 you are going by path A, and from state 2 to state 1 you are coming by path B, as shown here in the presentation also. And there is an alternative path through which also you can come to state 1, that is path C. That is path C. Now, here in this case, if we do the cyclic integral of this process 1A to B1, then integral of delta QA from 1 to 2 and 2 to 1 delta QB is equal to integral of 1 to 2 delta WA and 2 to 1 delta WB. So, work and heat interaction in this closed loop or a cyclic process is taken into account in this equation. Now, we will take another path, that is 1A to C1. In this path, again we will take the cyclic integral of heat transfer, that is 1 to 2 delta QA plus 2 to 1 delta QC is equal to 1 to 2 delta WA plus 2 to 1 delta WC. Now, we have these two equations. These two equations have been driven from the concept of the first law of thermodynamics. Now, if we take difference of these two equations, we will be getting this equation. And now if you look at this equation, if you again manipulate it, then you can have delta QB integral 2 to 1 minus integral 2 to 1 delta WB is equal to 2 to 1 integral of delta QC minus 2 to 1 integral delta WC, or delta Q minus delta W through B is equal to delta Q minus delta W through C. In similar fashion, we can prove that if there is another path D, in that case delta Q minus delta W D. So, all these three are equal. It means you choose any path, you choose B, C or D, the difference of delta Q minus delta W is going to be the same. This indicates there exists a property in the system, and this property is later known as internal energy of the system. It is total energy of the system. It involves everything. The difference in kinetic energy, potential energy, rotational energy of the atoms, everything it involves. And normally in the system, because we are dealing in the macroscopic level in the thermodynamics, so finally for a closed system, for the first law of thermodynamics, it turns out to be delta Q minus delta W is equal to du. Okay, because these three expressions are equal, it means irrespective of the fact you choose path B, path C and path D, you will be getting the same value. It means this value, this change in value is independent of the path you have chosen to arrive state 2 to state 1, and this value is nothing but the property of the system, and this property is internal energy of the system. So, the internal energy of a closed system remains unchanged if the system is isolated from the surroundings. It also says that a perpetual motion of machine of first kind is impossible. Now, a perpetual motion machine is an imaginary machine, and the first kind of perpetual motion machine means a machine which gives constant output without any input, and it works for an infinite time. It gives perpetual output without having any input, and this machine is not possible, because when we say delta Q minus delta W is equal to du, perpetual motion output you may be getting, but without any input. So, this is 0. At the cost of internal energy you will be getting output, but this cannot be done for infinitely long time. For a short period it is okay. For infinitely long time you cannot run a perpetual motion machine. So, the perpetual motion machine of the first kind, the machine which gives perpetual output without having any input, is not possible. Now, in fact I will explain you, there are three types of perpetual motion machines: first kind, second kind and third kind. Now, the second kind of machine is that machine which has 100% efficiency. So, that is violation of the second law of thermodynamics. So, any machine cannot have 100% efficiency. It means a machine cannot draw certain amount of energy from the source and do equal amount of work. That we will discuss during the second law of thermodynamics. And there is a perpetual motion machine of third kind also. It means the machine which does not have any friction losses, and it has perpetual motion by the inertia itself. So, all the machines are having friction losses and other damping effects. So, no machine is possible which has no friction and no other damping effect, and it runs by its own inertia. So, these are three perpetual machines. They are in fact imaginary machines, and for the first law of thermodynamics we can draw that the first kind of perpetual machine is not possible. Now, for the closed systems there are certain thermodynamic processes. One is isothermal process. Now, if you take isothermal process, the temperature remains constant. If you draw a PV diagram of an isothermal process, it is going to be like this. It is a hyperbola. Temperature is constant. Now, if we increase the temperature, we will be getting another curve, and this curve will be parallel to this curve. These two lines will not cut each other. And for isothermal process, the relation, ideal gas relation, is PV is equal to constant. Now, the second process is isobaric process. Isobaric process means constant pressure process. So, if the pressure is maintained constant throughout the process, that is known as isobaric process. Similarly, the third kind of process is isochroic process. In isochroic process, the volume remains constant. So isobaric process, the pressure remains constant, and isochoric process, the volume remains constant. Now the third process is polytropic process. The polytropic process, because these processes we will frequently come across when we will work on refrigeration and air conditioning. So state 1 to state 2. Polytropic process follows the law PV raised to power n is equal to constant. Now adiabatic process and isentropic process, they are also type of polytropic process, but adiabatic process is special type of polytropic process where there is no heat transfer across the system boundary. So if you look at the polytropic process, if you apply the first law, delta Q minus delta W is equal to du. So delta Q is equal to delta W plus du, and here we will say that it is integral of PdV system 1 to 2 plus du, and if we integrate using this, if we integrate, we will be getting P1 V1 minus P2 V2 divided by n minus 1 plus Cv T2 minus T1. Or if you want, if you write in a differential form, Q is equal to R T1 minus T2 divided by n minus 1 plus Cv T2 minus T1, or we can write Cv minus R by n minus 1 multiplied by T2 minus T1. Now in this case, this is the heat transfer in polytropic process. Now in this case, suppose if I take n is equal to gamma, when I take n is equal to gamma, R by gamma minus 1 becomes Cv, and when this becomes Cv, the heat transfer is 0. So in a polytropic process, so in a adiabatic process where gamma is equal to, for air, for example air, gamma is equal to 1.4. So when and it is a ratio of Cp and Cp, specific heat at constant pressure and specific heat at constant volume. The polytropic process becomes adiabatic process, there is no heat transfer. In isentropic process, it is clear from itself, isentropic process entropy remains constant, but they are different. In adiabatic process, though there is no heat transfer across the boundary of the system, but internal friction losses may take place and entropy may change. So adiabatic process is not necessarily an isentropic process, only reversible adiabatic process. Reversible adiabatic process, that process in which there is no friction loss. So reversible adiabatic process is an isentropic process, and in isentropic process also there is no heat transfer, as it is clear from the name itself, the entropy remains constant, so heat transfer is 0. We will discuss about the second law of thermodynamics. Second law of thermodynamics has two statements. One is Kelvin-Planck statement. This statement says it is impossible to construct a device that will operate in a cycle and produce no effect other than the rising of a weight and the exchange of heat with the single reservoir. It means it is not possible to draw certain amount of heat, that is, let us say 100 joules of heat from a reservoir and do equal amount of work. It is not possible. That is a statement by Kelvin and Planck. Another statement is by Clausius. The Clausius statement says that it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer of heat from a cold body to the hotter body. It means heat by itself cannot flow from lower temperature to higher temperature or cooler body to hotter body. So if you want to make heat flow from low temperature to high temperature, external work is required. These two statements, Kelvin-Planck statement and Clausius statement, both the statements are addressing the second law of thermodynamics. It means violation of one statement should automatically lead to the violation of another statement. Let us assume that there is a violation of Clausius statement. So in that case, suppose there is a reservoir of temperature Th. The thermal reservoirs are the bodies of infinite thermal capacity, so that if you draw certain amount of energy from these bodies, the temperature of these bodies does not change. So there is a device which is extracting certain amount of heat, that is QH, from here and rejecting QL here in the lower temperature, and this device is doing work is equal to QH minus QL, right. Now another device which is violating the Clausius statement, it means QL from lower temperature is flowing to higher temperature without any external assistance. Now if we club these two devices, then we will be getting a scenario like this. TH, there is a device giving the output QH minus QL, which is drawing heat QH minus QL. So QH minus QL, because QH is coming from the reservoir and QL is going back to the reservoir, so net heat coming from the reservoir is QH minus QL. However, in this case QL heat is coming to the reservoir and QL heat is leaving the reservoir, so net heat transfer to the reservoir is 0. So if we are drawing QH minus QL from high temperature reservoir, then we can produce QH minus QL amount of work, that is violation of Kelvin-Planck statement. So violation of Clausius statement will automatically lead to the violation of Kelvin-Planck statement. Now we will assume that there is a violation of Kelvin-Planck statement. So when there is a violation of Kelvin-Planck statement at high temperature reservoir, QH amount of heat is taken and work is done by in the QH amount, and 0 heat is rejected to the reservoir. This is violation of the Kelvin-Planck statement. Now we have a device which is pumping Q amount of heat, and if we connect this with this device instead of having output on this side, if we couple them, then this is going to be W is equal to QH, and heat transmitted to the high temperature reservoir will be QH plus Q. Now we are coupling these devices, so Q amount of heat is getting transmitted from lower temperature to higher temperature without any external work. This is leading to the violation of Clausius statement. So it is proved that if you violate one statement, it will automatically lead to the violation of another statement. Now there is often confusion about the gases and the vapor and their behavior. A vapor does not follow the ideal gas equation. If you look at the PV diagram of a typical PV diagram, here quality is 0, this is pressure, and this is volume, and this is quality is 1. If you look at the typical PV diagram, at constant temperature, characteristic line will be like this. This is temperature is equal to constant. Now if you increase the temperature, the line will also shift. You keep on increasing the temperature, the line will keep on shifting, and during this region, the vapor does not follow the ideal gas equation, PV is equal to RT. And the maximum deviation in single phase is here when the line becomes horizontal. This is critical point. Beyond critical point, if you draw the curve you will be getting like this, and when the temperature is greater than 2 times the critical temperature, in that case you will be getting the curve which follow the PV is equal to RT. So a vapor can be considered as a gas when the temperature of the vapor is 2 times the critical temperature, as it is shown in the slide also. We have taken example of water. So water temperature, critical temperature of water is 373.95 degrees centigrade, and in Kelvin it is 647.1 Kelvin. So water can be considered as a gas at 2 times of critical temperature, that is 1294.2 Kelvin, which turns out to be 1021.05 degrees centigrade. Now, any vapor which is below 10 kilopascal pressure can also be considered as a gas. So, in air conditioning processes, the presence of water vapor is considered as gas. So, water vapor is treated as a gas because partial pressure of water vapor in air is always less than 10 kilopascal. However, in the case of a steam power plant where the pressure is 10 megapascal or 20 megapascal, the maximum temperature does not exceed 640 degrees centigrade. So, water vapor is not considered as a gas. That is why we need steam tables for the calculations for steam power plants. Now, this is over here with the concepts of the thermodynamics. In the next class, we will take up the introduction of refrigeration.